Welcome to our Sednol today. We are very happy to have with us Delia Schiera from University of Lisbon. She will be, well, thank you, Delia, for accepting our invitation, and she will be talking about a weighted anisotropic spectral optimization problem arising in population dynamics. Thank you, Delia.
Okay, thank you very much. Okay, first of all, I wish to thank Alberto and Monica for the invitation. I'm really happy. It's a pleasure for me. And well, I really hope that I will have soon the opportunity to be there in person in Mexico. And okay, so thanks a lot. And today I'm going to present some results I obtained in collaboration with Benedetta Pellacci and Giovanni Pisante, who are both at Università della Campania in Italy. And well, this problem is an optimization problem which arises in population dynamics. So the idea of the, the idea of the talk is to start with the classical case, just to give some motivation and introduce like the main known results in this context. And then our work will be to, let's say, substitute the classical diffusion induced by the Laplace operator with a different diffusion, which is going to be an anisotropic diffusion. So the second part of the talk will be to introduce this new operator. And then I will do exactly what I just said. So I will try to put this different diffusion in the problem I introduced in the first part and see what happens. And so part 4 and part 5 are going to be our main results and some work in progress, what we are doing right now. And I hope that we are going to conclude soon. Okay, so let's start with the introduction. So let's say this is the problem with which you start with, and it is the diffusion logistic equation. So if you're not familiar with this kind of problems, don't get scared. So the idea is to model a population. So you can think of animals in a region omega. Omega is going to be a bounded domain with Lipschitz regularity. And U is going to represent the density of this population. And so, as I said, this population is going to move around with a diffusion induced by the Laplace operator. So you can think of a random walk process with the diffusion rate D. In the nonlinear part, which is the logistic nonlinearity, well, you have these two terms here. The C describes the effect of crowding. So obviously, if the population gets too big, then this is bad for the population. Whereas the function M, which is going to play a crucial role in our analysis, describes the allocation of resources. So it's going to be an L infinity weight changing sign. And well, if M is positive in a point, this means that in that point of the region, the situation is favorable to the population. Whereas if M is negative, then you have an unfavorable situation in that point. So you have to impose some conditions. So this weight M is going to be in a suitable class, but you can just think of L infinity weight, which changes sign. Good. And what about the boundary conditions? Okay, we are going to consider Robin boundary conditions. And let's say the two limit cases are the case K plus infinity, which corresponds to Dirichlet boundary conditions. So in this case, you are assuming U equals 0 at the boundary. And this means that the region outside omega is lethal for the population. So if an animal reaches the boundary, then it dies, basically. Whereas the other, let's say the other extremum is the case K equals 0. with Neumann boundary conditions. And in this case, the boundary is like a barrier. So if the population gets close to the boundary, it is naturally led to go back inside the domain. So here I put just a couple of very basic standard references, but the literature for this kind of problems is huge. And I would like just to mention what we are going to use, what is going to be important for our work. So it is known that, let's say, if you consider the steady state equation corresponding to the diffusive logistic equation, you get well something like this. And it is known that this problem has a unique positive solution, which is an attractor for solutions of the diffusive logistic equation if the diffusion rate D is below some suitable threshold. Whereas if you are above this threshold, then the trivial solution is an attractor for solutions of the diffusive logistic equation. So what does it mean? It means that if D is below this threshold, then the population will survive. Whereas if D is above this threshold, then the population will go to extinction. So it is obviously interesting to understand better this threshold. And this threshold is the inverse of the positive principal eigenvalue of the corresponding, let's say, linearized problem. So you take this problem, you just consider, let's say, the linear part. And so this is going to be the first positive eigenvalue of the Laplace operator with Robin boundary conditions with this weight m, which, as I said, is going to play a crucial role. So just to give a couple of facts on these principal eigenvalues, because of course you know about eigenvalues of the Laplace operator, but maybe you are not familiar with the case of weighted eigenvalues. So the idea is to define a Rayleigh quotient. So it is completely analogous to what you would do in the classical case. And it is well known that this value is attained. So you have an existence of an eigenfunction. This lambda is simple in the sense that there is only one principal eigenfunction to a multiplicative constant. And the principal eigenfunction is the only positive eigenfunction. So any other eigenfunction is going to change sign. And another thing which is, well, a bit stupid, but it's going to be different in our situation is that here, once you have a solution, also minus u is a solution. So any eigenfunction of lambda m, we know that as fixed sign, and we can choose this sign to be positive. But this is not going to be the case in our situation. Okay, so let me just sum up. So we started with this diffusive logistic equation. And what we know is that below this threshold, we have survival, above there is extinction. So what we would like to do is to, let's say, maximize the chances for the population to survive, depending on the allocation of resources, which is modeled by the weight m. So the idea is to maximize this 1 over lambda m as m varies in the class. So correspondingly, we wanted to minimize lambda with respect to the weight m. So this is now an optimization, a spectral optimization problem. And this is going to be our focus. This is just some very partial bibliography. I would like just to mention that in the one-dimensional case, the situation is, I would say, clear. It is completely solved. Whereas in the higher dimensional case, there are many surprising results in the sense that in some situations, let's say from a numerical point of view, you would expect something to happen, and then actually this is not the case. And there are also many, many open questions, so this is far from being solved. And there are a lot of related works with different, let's say, optimization problems. So you optimize with respect to other parameters. And there is this line of research, which is considering different diffusion operators and see what happens. And our work goes exactly in this direction. So we are going to substitute the Laplace operator with a different operator, which is going to be the anisotropic P Laplace operator. Okay, so let me introduce our diffusion operator. So this is going to be the operator we are going to consider. The P plays exactly the same role as in the P Laplacian. Okay, so you can think for simplicity of P equal 2. And of course, the main feature of this operator is this function h, which plays the role of the Euclidean norm. So basically, we are measuring distances with respect to a different norm, which is going to be the anisotropy in the problem. And actually, I said a norm, but this is not really a norm. So we are assuming that it is positive, that the ball is uniformly convex, but we are not assuming that H is homogeneous, but only positively homogeneous, and this will make a big difference. So in general, H is not even in our situation. And here I put some basic references on this kind of operators, so in different contexts with respect to our context. This is just, let's say, standard properties of these operators. And let me say just that there are other type of anisotropic operators which we are not going to consider, but in case you find in the literature anisotropic operator, not necessarily is this one. And well, what about if you take this H, this basically as level sets, ellipses. So in a sense, this model a population which moves with different probabilities depending on the direction. So in this situation, the population will move faster in the horizontal direction than in the vertical direction. And actually, there are also other applications in metallurgy, crystallography. So these kind of operators appear in many different contexts. But just since we are thinking of a population, in our context, this is going to model a population moving in different directions with different probabilities. And just to be a bit more clear on that, so we all know that the Laplace operator can be modeled as the limit of a random walk. So basically, you write the probability of being in a point, in this point blue, at a time t, as 1/4 the probability of being in this point, 1/4 being in this point, and etc. So it is basically the probability here depends in the same way with on the probability of being in one of the green points at the previous time. And then you take the Taylor expansion and you take the limits and you get the Laplace operator. In this case, in the case of the anisotropic Laplace operator, you also need to consider what happens in the red points. So this is the first difference. And actually, you weight in a different way the probabilities of being like in the points in the northern part with respect to the points in the southern part, let's say. So you take a weighted average of probabilities of being in different points in the neighborhood of your point. So that's more or less the idea which is behind these operators. And now let's try to put this operator in the problem I introduced in the first part of the talk. So this is, let's say, the translation of the problem in this new context. So of course you have to put a p in the right-hand side just because you want the same homogeneity on the right and the left-hand side, exactly as in the p Laplace operator. And of course, it changes a bit also the boundary condition because this comes from an integration by parts of the operator. But this is really the translation. We just put the new operator in place of the Laplace operator, and we are considering the natural problem in this context. And the weight m is going to be exactly in the same class as before. So it's going to be sign changing weight in L infinity with some bounds from below and above. Okay, so since in the classical case, the spectral properties of the Laplace operator played a crucial role, we expect something similar also here. So let me say a couple of words on the principal eigenvalues for this operator. And what it turns out is that since we are not assuming H to be even, then in general, you have two positive principal eigenvalues. This is not the same as in the Neumann case, in which you have like the first one, which is 0. I'm saying that you have really two different eigenvalues, which are both positive, one with a positive eigenfunction and the other one with a negative eigenfunction. Since H is not even, it's not true that once you have an eigenfunction, minus u is still an eigenfunction. This is not the case. So positive and negative functions are not, let's say, interchangeable, and you have to be careful. And how do you get these two eigenvalues? You take the infimum of a Rayleigh quotient, but on a cone. So you take the infimum over the u, which are positive, on the cone of positive functions, and you get this lambda plus. And if you do the same with negative functions, you get lambda minus. And in general, these two are different. And yeah, if you are familiar with the Pucci operators, fully nonlinear operators, this is something which is similar in a sense. There are some similarities, but of course, these are completely different operators. And well, the first thing we did was to prove some basic properties of these eigenvalues. So as I said, the lambda plus is going to be attained by a positive function, which is going to be an eigenfunction for your problem. And this is actually the unique positive eigenvalue with positive eigenfunction. And analogous results also for lambda minus. But we are actually going to focus on lambda plus for a reason that it's going to be clear now. What we proved is that you have a similar phenomenon as in the classical case, in the sense that your reaction diffusion problem here, it's going to be, let's say, to lead to survival of the population if D is below a critical threshold, which depends on this lambda plus, in the sense that there exists a unique positive solution to the anisotropic reaction diffusion problem if and only if D is below this value. Of course, you have something similar for negative solutions. So you have a unique negative solution if D is below the similar threshold, but with the lambda minus in place of lambda plus. But since we are thinking of U as a density, so we are more interested, at least from an applicative point of view, to U positive. So we are more interested in the case of lambda plus. But from a mathematical point of view, it's of course interesting also to consider lambda minus. And this is actually something that we did, and I will say a couple of words at the end. So from now on, our problem is to try to minimize lambda plus with respect to the weight m in the class of weights that I introduced before. Okay, so what can we say of this minimization problem? So the first thing that you can prove is that this minimization is actually attained by bang-bang type function. So what is a bang-bang type function? It is an L infinity function which only assumes two values, a positive value and a negative value. So this is a stupid example just to give you an idea in dimension 1. So these bang-bang functions are completely, let's say, defined once you define a set D. So this is basically, once you know where is your set D, you also know how this M is going to be. Because M is going to be, let's say, between two fixed values. So you already know that let's say, when this is positive is equal to 1, and when it is negative is equal to minus beta. But okay, so these functions only assume two values. And the first thing is that optimizers for lambda plus are all of this type. So basically you are translating everything into a shape optimization problem, because now the natural question is, can we select one or more among these Bamberg type functions, which is going to be better for the population? And this corresponds to choosing the best set among all possible sets in order to improve the chances for the population to survive, or from a mathematical point of view, in order to minimize the lambda plus. Okay, so that's exactly what we did next. So trying to understand where the optimal set is. And in this case, so far, we restricted ourselves to the one-dimensional case, and we are now working on the high-dimensional case. So let me first explain what happens in the one-dimensional case. In this case, H has necessarily this form. And well, the fact that A is different from B is crucial, because otherwise you basically have the modulus, a constant times the modulus. So it is not interesting. So if you want to see an anisotropy in this setting, you really need to assume H to be not even. So this is why we did everything for non-even anisotropies. And our result is as follows. So in the case of Robin boundary conditions, the optimal sets are going to be close to one of the extremum. And this is going to depend from the values of A and B. Whereas if A is equal to B, so in the isotropic case, both sets are optimal sets. Whereas in the Dirichlet case, you have an explicit expression for this D, which of course depends on A and B. So let me just give a couple of drawings just to explain what I mean. So this is the Neumann case. These are the two best weights in this case. If A is bigger than B, then you have the situation on the left side. If A is below B, then you have the optimal weight is going to be the one on the right-hand side. And if A is equal to B, they are both optimal. Whereas in the Dirichlet case, you have this situation, the set D is going to be contained in 0, 1, so away from the boundary. And these D1 and D2 are explicit. And if A is equal to B, this D is going to be exactly centered in 1/2. Okay, so this is what happens. And in the next, I don't know, 10 minutes, I would like to say a couple of words on the proof, just on the main tools we are going to use. And well, the basic tools are rearrangement techniques. And we are going to use basically two kinds of rearrangement, the monotone rearrangement and the anisotropic rearrangement. And let's say that the most technical part was to prove some suitable polytype inequalities for this kind of rearrangement in this context of anisotropic operators. So let me just say a couple of words on these two rearrangements in case you are not familiar with it. So this is the formal definition of the monotone decreasing rearrangement. But okay, the most important thing is that this rearrangement satisfies this property here, which means that superlevel sets of U and its rearrangement have the same measure. So this is the equimeasurability property, and this is crucial in these rearrangement techniques. And just to give an idea what we are doing, so you take your function U and you cut it at level T, and you see what's the measure of the sets of point such that U of that point is above T. And now you put this set here close to 0. And this gives you a new function which has this nice property, and it is decreasing. Of course, you can do also the same thing with the increasing rearrangement, just putting everything close to 1. Okay, so as I said, the crucial part is to prove suitable inequalities. So the undeliverable inequality was already known, and we proved a Pauli inequality in this context of anisotropic operators. It was known for the isotropic cases, so for the case of the Laplace operator. And it turns out that the situation is a bit more delicate than what we expected. And the result depends actually on the value of u in 0 and 1. So if u in 0 is bigger than u in 1, then you have that, let's say, this integral hp of u prime is above the same integral, but with the monotone decreasing rearrangement. Whereas if u0 is below u1, you have a similar thing, but with the increasing rearrangement. So the crucial point here is that if A is equal to B, so in the isotropic case, the right-hand side here is the same if you consider the decreasing or the increasing rearrangement, because let's say a change of sign in the derivative of u doesn't change the value of h to the power p. But in general, this is not the case. So this actually was a bit surprising, but also a bit technical to prove. And let's say if equality holds, then u is monotone. So what we actually proved is this proposition here, which is actually interesting also in the isotropic case. So you have the inequality you want plus some error term, which depends on, let's say, the points in which u is above u0 or below u1. And once you have this, this gives you immediately the inequality, and also the equality case. This part here is crucial in order to prove the equality case. But anyway, this was just to give an idea. And okay, this is just what I just said. So basically the error term depends on what happens in this area here and in this area here. Okay, the other rearrangement we used is the anisotropic rearrangement. Okay, here I put all the mathematical definition, but maybe it is just better to give a couple of drawings to see what we are going to do. So as before, you take your function, you cut it at level t, and you take the super level set. So there's the set of points such that u is above t in that set. And now in the classical isotropic case, so the symmetric decreasing rearrangement, you just put this set here centered at 0. So what we are doing here, you're just taking the ball centered in 0, which is in this case an interval, but it is an isotropic ball centered in 0 with the same measure of the superlevel set. Now, in the anisotropic case, you do basically the same thing, but instead of isotropic balls, you are taking anisotropic balls centered in 0. So you are weighting differently what happens on the right-hand side and the left-hand side. So you're going to have something which is not symmetric from a Euclidean point of view, but still increasing and decreasing. And also in this case, it was important, of course, to prove the undeliverable inequality actually was already known, and the Pauli inequality. And for the Pauli inequality, there are some, let's say, known results for the even case or for higher order dimensions. But okay, we proved the one-dimensional case with h not even necessarily. And well, the inequality also for any u in W1P, what we actually struggle a bit to prove was the equality case. So if equality holds here, then u is equal to its anisotropic rearrangement. But you need some extra hypothesis of regularity, and also this red hypothesis here, which tells you that the flat zones of u are finite. This is a bit too much. I mean, it is enough for our purposes, but it is a bit too much because usually what you prove is that let's say if this set has measured 0, then you get the equality case. But okay, that's what we managed to prove. But in any case, you need something like that as an hypothesis. And this is an example to convince you that this is the case. Even in the isotropic case, in the classical isotropic case. So if you take a function which looks like this, you have a flat zones, which is not trivial here. And you can just make computations and verify that indeed this U verifies the equality in the Pauli inequality, but evidently U is not equal to its symmetrical arrangement because this is not symmetric. And why? Because this zone here, you don't see it in the integral here, because basically here it becomes 0, so you don't see it. And so you can put it anywhere in U, and so you don't have uniqueness anymore. So that's more or less why this thing of the flat zones is that important in the equality case. Good. And now the idea of the proof, just in a couple of slides. And actually, once you have these tools, it's super standard, super easy. You just use the definition of lambda plus as an infimum of Rayleigh quotients. And as competitor, you use a function phi, which is phi star, which is given by the increasing rearrangement of your eigenfunction up to some point, and then the decreasing rearrangement in the other, let's say, in the other half of the interval. And you use Pauli inequality in the, let's say, in the numerator, and Hardy-Littlewood inequality in the denominator. And since lambda plus is the optimal one, then you get a chain of inequalities which are actually equalities. This gives you the equality in the Pauli inequality for these functions. And then you use the characterization of the equality case, and you immediately get that your eigenfunction was increasing and decreasing. And then you can use the anisotropic rearrangement, because now you know that since your eigenfunction is only increasing, decreasing, and actually you can also prove that this monotonicity is strict, then you have a finite number of critical points. So that condition of flat zones is actually satisfied. And you can do basically the same thing, but with this anisotropic rearrangement. And once again, you can use the equality case in the Pauli inequality, and you get the phi is equal to its anisotropic rearrangement. So it is just using the tools I presented up to now, and to exploit the equality case in the Pauli inequality in order to prove some rigidity result on your eigenfunction. So that's more or less the idea. But okay, maybe I will skip the part of the minimization of lambda minus, because okay, you can just say something also for the lambda minus from a mathematical point of view is obviously interesting. So we also proved some results of optimization for the lambda minus, and some, let's say, a relationship existing between the optimal eigenfunction, the optimal weight for lambda plus, and the optimal one for lambda minus. But I would like to say maybe a couple of words on what we are doing and on the higher dimensions, which is obviously interesting. Now that we know what happens in the dimension 1, we would like to say something about what happens at least in dimension 2 or more. And so we are trying to consider some specific cases, because as I said, also in the isotropic case, there are still many, many open questions. So it is a bit too much to expect to be able to solve everything in an isotropic case, of course. So we are just trying to see what happens in some specific situations. So first of all, what happens if you take a cube with the Neumann boundary conditions? So in the case of the Laplace operator, the optimal set is in one of the angles. And all the angles are equivalent with respect to the optimization problem. In the anisotropic case, well, if h is even in each variable, you have basically the same phenomenon. But actually the proof is a bit, say, there are a lot of small technicalities that we are trying to solve. I think that we are almost there. So basically, you rewrite your problem as a problem with the periodic functions in R2. And for this, it is obviously crucial to have Neumann boundary conditions in order to duplicate your original cube. And then you use a Steiner symmetrization, which is, let's say, the extension of the symmetric decreasing rearrangement in higher dimensions, in the sense that you are considered the symmetric rearrangement in each component. And now you need a Pauli inequality and the equality case for the Pauli inequality. And there was this result by Cianchi-Fusco for, let's say, a similar situation, but with the Dirichlet boundary conditions. So it was a bit different. We had to let's say, to adapt everything to the periodic setting. And of course, this requires some condition on flat zones, exactly as in the one-dimensional case. And you have to prove that your eigenfunction satisfies this condition on the flat zones. So the basic structure of the proof is morally the same, but you have a lot of small technicalities you have to fix. And well, I already said these remarks that all the angles are equivalent in the sense that if you have an optimal weight, also this transformation, this, let's say, reflection of M is still an optimal weight for your problem. Now, what happens if you take an H which is not even? So this is the model case. And of course, you can do a bit something a bit more general, but let's say this is the model case. And here you don't have just the problem that H is not even. You also have the problem that H doesn't have the same regularity as in the standard case. So this is not C2 outside 0, but only C1, because in one of the axes, this is going to be just C1 and not C2. And this creates a lot of problems because, let's say, in the classical case, the first step is to prove that there are no flat zones. And actually, in this case, you can't use the standard results because they let's say they rely on the regularity C2. So we first had to prove some results in order to let's say to exclude the flat zones, or at least to prove that the flat zones have zero measure. And of course, you need an adaptation of Pauli inequalities and equality case in this situation. So you solve the same problems as above, but you have this extra regularity problem, which is not trivial. And the interesting thing here is that the optimal weights are still in the angles. So the optimal sets are touch the angles, but not all the angles are equivalent. This is exactly what happened in the one-dimensional case, in which you had two different weights, one for the case A bigger than B and one for the case A lower than B. And also in the high-dimensional case, not all the angles are equivalent. So the anisotropy chooses one or more of the angles depending on the situation. And what about the Dirichlet conditions? So for the Laplace operator, it is known that the optimal set is a ball if and only if omega, the domain, is a ball. And we expect something similar also in the anisotropic case, in the sense that one would expect that if, let's say, the optimal set is an anisotropic ball, if and only if omega is an anisotropic ball. And one direction is, I would say, easy. And there are already some results in this direction, in the sense that you have a Pauli inequality for this situation for the even case. So we just needed to adapt everything for the non-even case, but it is doable. So you prove that if the domain is an anisotropic ball, then also the optimal set has the same property. But the vice versa looks more difficult, because the proof for the isotropic case relies on the explicit expression of the Laplace operator, and also on analyticity of the coefficients. And another important thing is that the rotation, the invariance and the rotations seem to play a role. So we managed so far just to consider the ellipses. And one thing we would like to do is actually to try to see what happens at the limit. So if you take, let's say, the limit as the measure of the optimal set goes to 0, then you expect that the boundary of the domain would not play a crucial role. So you expect to get some results, at least at the limit, at least from an asymptotical point of view. So this is something we would like to try also. And well, there are still many open questions, still a lot of things to do. And so if you are interested, come and work with us. And thank you very much.
Thank you very much, Delia, for this very nice seminar. Are there questions for Delia? Please, Juan Carlos.
Hi, thank you very much for your talk. I have one question here because you're saying that you obtain a Pauli-Segou inequality, but in dimension 1, and you're trying now to see what happened in bigger dimensions. Is that correct? Or you have already had the Pauli-Segou inequality in higher dimensions?
Okay, we have okay, it depends. I mean, for the case of the Steiner symmetrization in higher dimensions, so this is the symmetric decreasing rearrangement in each component. We have we have a Pauli inequality. Well, it was already known with this paper by Cianchi Fusco in the case of zero boundary conditions. So let's say you assume 0 to be the function to be 0 outside, let's say, a compact support. And what we did was to extend to the periodic setting. So you have periodic functions.
So my question is, as the Pauli-Segou inequality is deeply related with the isoparametric problem, what is the isoparametric problem here behind this inequality? What is happening geometrically in this case?
Well, maybe it is easier to see it with the let's say the anisotropic symmetrization, which is the extension of the Schwarz symmetrization. Maybe it is easier to see it from that perspective, because in that case, well, in a sense, you first prove that the equality forces the level set, the super level sets, to be balls. In this case, anisotropic balls, but in the classical case, you have balls. And then you prove that they are all centered in the same point. So this is more or less the idea of the proof. And the isoperimetric inequality gives you the fact that you have balls actually. And here you have anisotropic balls. So you are measuring differently the distances. You're using a different norm in a sense. I don't know if I reply.
The isoparametric profiles are these kind of weighted balls.
Exactly.
May look like to get a picture. It may, as you talk at the beginning, they could
like
look
ellipses.
like ellipses. Yeah. So
Yeah,
you're foliating Rn with ellipses. Okay.
Yes, exactly.
Okay. That's interesting because those profiles are really different. Thank you very much.
Thanks.
Thank you. Are there? Yes, Sean, please.
Yeah. So you said in higher dimensions, when you were looking at the anisotropic version, I think you had an equation written where you just had the two dimensions, that you sort of lost C2 regularity, and that this was running into some problems. And I was just curious if you could expand upon this a bit more, because if I read this correctly, right, like you only lose C2 regularity in a very small set. And I was wondering how that was screwing up the sort of lack of flatness arguments in your Pauli-Segou type argument.
No. Yeah, indeed, this is exactly what happens in the sense that, let's say, you can't use the classical result, which is for C2 functions, but you can adapt the proof in order to consider also this case, and this is what we did actually. So at the end, yes, this you lose the regularity just on one of the axes, and this is not enough to create a problem. But yes, from a technical point of view, you have to prove it. That's the only thing.
Thank you so much.
Thanks.
Thank you. Are there more questions or comments? So I have some questions. So I like very much this interpretation of the age in terms of the probability of a population moving. So for your particular age that you took in dimension 1, where you have a parameter A and B, is it as simple as saying that the population moves more in the direction where the A is larger? So is this like this direct interpretation?
Well, no, not really, because it's actually, I mean, the H depends on the derivative of U.
Exactly.
So it's a bit, it's not just that yeah, I mean, the probability yeah, I a bit cheated because actually the probability of being in one point depends on what happens in the neighborhood, but also, I mean, it depends on the derivative of U in that point. So it's a bit different. It's like you are, let's say, you probably this would model also something like traffic models, because if you see that there are a lot of cars in a part, so the population is getting bigger and bigger, you have the derivative which is positive, and so you are led to go in that direction or to avoid that direction. So this is a bit more delicate than that, actually. Yes.
Okay, I see. Thank you. I have plenty of questions. So I also like very much this result on the inequalities with rearrangements, and you say that this depends on the value of U0 and U1. No, you had this assumption U0 larger or equal U1, and only under this assumption this would happen. So you have a counterexample if this doesn't hold. So if U0 is less than U1, you know that the inequality is false.
Wait, let me think about it. If U0, well, yes, I mean, if U0, if you take an increasing function, you take U, which is increasing, so this is false, and this is not going to be true if, let's say, A and B are in the wrong direction. Let's say here you would have the U star, the increasing one, and here you would still have the decreasing one. And this, at least in one dimension, is going to be A to the power P, and here B to the power P. So if A is smaller than B, then you have a contradiction.
Okay. So you have this proposition only for this explicit case of H.
This is in dimension 1, yes. This is dimension 1. And no, the H, I mean, wait, this H is actually all the H which satisfy our assumption in dimension 1
are of this type.
Are of this type, yes.
Okay. Okay, I see. And so related to what Juan Carlos was asking, in terms of these anisotropic symmetrizations, you would have a Faber-Cran type inequality, like the one that minimizes the eigenvalues are anisotropic balls?
Yeah, I think there is something in this direction, but let me think. I think there are some results. I think there are some results in this direction, but right now I can't give you a precise reference. But I'm quite sure that there are results in this direction. Yes.
Thank you. And my last question. So you have studied this in an interval, and you have studied this in a cube. So as a conjecture for a general domain in R2, a general bounded smooth domain, would you expect that? But would you expect that the set D would be close to the point of highest curvature?
Yeah, that's yeah, that's actually something. I mean, probably it's hard to say just you take a set and you prove that it is actually in the point of maximal curvature, because I think this is not known also for the Laplace operator. I mean, for the cube is known, for some specific cases it's known, but in full generality, I think it is not known. But what we would expect to do is to do something at the limit. So if the measure of the optimal set goes to 0, then there are some results by Benedetta and the collaborators, Dario Mozzoleni, Gianmaria Verzini, etc. And they do the same thing, but with the Laplace operator. And they prove that actually the maximum, the optimal set concentrates in a point of maximal curvature. So here we would expect something probably which depends on the anisotropic curvature, of course. So we would expect it to be concentrating in the point of maximal anisotropic curvature, which in general may not be the maximal curvature in the isotropic sense, of course.
That's very interesting.
That's
Thank
what we
you.
expect.
Are there more questions or comments?
I have one more question.
Yes, Sean, please.
You said in your intro that you have this dichotomy between when D is above the reciprocal of your base eigenvalue and when D is below. But like, what happens at that value? Is there
actually, I don't know. Honestly, I don't know what happens exactly. I don't know if it is like one of the two is bigger or equal, lower or equal. I would need to check, actually. I don't know. I don't remember. I'm sorry.
No, it's okay. Thank you. It was an absolutely wonderful talk. It was very interesting.
Thanks.
So the question is if at equality you have extinction or persistence,
Yeah.
right?
Or non-unique solution. I mean, just trying to read the statement.
Maybe it depends on the initial condition. I mean, for the parabolic problem and for the elliptic, I don't know. Yeah.
No, I don't remember, honestly. I don't know.
Yeah, maybe it depends on the parameters of the problem. It's more delicate in that case.
Yeah,
Well,
makes sense.
are there more questions? If that's not the case, let us thank Delia again. Thank you very much.
No, thank you very much for the invitation. Thanks.